to formula in one-dimensional case. So the last session we saw that some property of the differential of Brownian motion. And when I am saying the differential of a Brownian motion, you have to keep in your mind that such a thing does not make sense. So I need to emphasize this a lot so you remember. However, it's a notation that's useful, we are used to, and therefore we apply it. So one important property that we saw was that ddt squared was equal to dt. Okay? And the purpose of today's lesson is to find the differential of not just a Brownian motion, but a function of a stochastic process. Okay, so that is the goal of today's lecture. So let's say we have a process dxt equal to, I'll try to use the same notation, zt dt plus yt ddt. So let's say we have this process where zt is a function z of t and xt, and yt is also a function of t and xt. So zt and yt are processes, functional processes defined based on t and xt. And what we're looking for is to find the differential of f of xt. So what is this formula? And once we obtain this, then we call this one-dimensional Ito calculus, okay, or one-dimensional Ito process. And in some book also, this process dxt is called the Ito process. So how to do that? We start with Taylor expansion. So we will have the prime of xt d of xt plus half of f double prime of xt and dxt squared plus something that contains dxt to the power of 2. So this big O, which I don't define it formally here, in simple word it means that we have terms that all contain dx cubed. Okay? So this is by Taylor expansion. Now, in one-dimensional calculus, we know that we cannot ignore dx. So we have to count that. Now we will see that whether we should ignore or count dx squared. Okay? So let's just calculate dxt to the power of 2. So we have dxt zt dt plus yt d of dt. So make the square of this expression. We obtain zt squared dt squared plus 2 zt yt dt d of dt plus yt squared d dt squared. Okay? Now the first term is ignorable because we have dt squared times something, and by deterministic calculus we know that we can ignore dt squared. So this one is 0 plus. Now can we ignore dt ddt? If we can ignore dt ddt, then it doesn't matter what are these terms. These are 2zt yt times dt ddt. So we need to discuss whether we can ignore dt ddt or not. It's better, as in your book, it's better to write table. So here they say dt. Okay, by deterministic calculus, dt times dt is 0. So that's why we have 0 here. And you already know that dbt times ddt is dt, right? So we obtain that one. So for the moment, I need the middle term. So this term, the last one, would be yt squared dt. Okay? By this formula, ddt squared or ddt times dt. So what about dt times ddt? Can we ignore that or not? And And again, we use a very simple and understandable argument. It's not precise, but it will get us the result. So variance of dt dvt. So here dt is a constant, well, a deterministic differential, so we can take it out times variance of dvt. And variance of dvt is equal to dt, right? So we discussed that last session. So this is dt. Now dt times dt is 0 by deterministic calculus. So this is 0. Okay, so again, look, variance of dvt is equal to expected value of dvt squared minus expected value of dvt to the power of 2. So this one, we did the calculation, and we saw that this is actually dt minus expected value of dvt is 0, because that's a Brownian motion, so this is 0 squared, so we get, therefore, we get dt times dt, which is 0. Okay? So we have the variance of something, let's say a random variable, which is 0. Therefore, we know that dt dvt is constant. Okay? So not only it's deterministic, but also it is constant. So now we want to obtain the value of this constant. Take the expectation of dt dvt. So what is this? Again, dt, you can take it out, times expected value of dvt. Expected value of dvt is 0, therefore this is 0. So we have a random variable, which is a constant, and we know the expectation is 0, therefore it must be 0. So here we get that dt times dvt must be equal to 0. I think I made a mistake here. So this should be dt squared. So if we dt squared, anyway, it's 0. Once you take a constant out of a variance, you have to make a square. But in any case, it's equal to 0. Or you could obtain this by the definition of variance. So take expected variance of dt dvt to the power of 2 minus expected variance of dt dvt to the power of 2. In any case, you will get the same result. So now dt times dvt is 0, and therefore dv times dt is also 0. So any question about this argument? I agree that it's not exact, so nothing is really very rigorous here. It's just a simple way of understanding this equal calculus. Okay? So now that we know dt times dvt is 0, so the middle term is 0, and therefore we have dxt squared equal to yt squared times dt. And therefore we cannot ignore the square of dxt because we cannot ignore dt, right? So this second term here is not anymore ignorable. So in deterministic calculus, you could ignore that, but here you cannot because it's in the order of dt. Okay? So this is about the second term, so it's not ignorable anymore. But what about the terms that contain dx cubed? Can we ignore them or not? So let's say calculate dxt to the power of 3. So this would be dx to the power of 2 times dxt, right? Now dx squared was calculated here, so it's yt squared dt. So yt squared dt dxt, we have the stochastic differential equation zt dt plus yt dt. Now, can we ignore this or not? So we have dt times dt, which is 0 by deterministic calculus. And then we have dt times dvt. By this table, dt times dvt is also 0. So it would be 0 plus 0 equal to 0. So it's very interesting. We could not ignore the second term, but we can ignore the third term and beyond. So any term that contains dx squared can be ignored, because dx squared is 0, 0 times whatever is 0. Okay? So this third term here can be ignored. Right? Any question here? Therefore, our formula that we call equal formula would be d of f xt equal to f prime of xt dt plus half of f double prime of xt and d of xt squared. Sorry. Yes. So the cube term here can be ignored because we showed that dx cubed is 0. You might be wondering that what about dx4, dx5, and so on. But for instance, dx4 would be dx3 times dx. And because dx3 is 0, then dx4 is also 0. So maybe it's better to write it. So dx4 is equal to dx3 times dx, which is 0 times dx is u0. Okay? So we can say that dx to the power of j is 0 for j greater than or equal to 3. And therefore the rest disappears. And this is nothing but one-dimensional Ito formula. So this is Ito's formula in one dimension. Okay? So if you compare this with the deterministic calculus, you have one extra term, and that is the difference. So if we compare it with d of fx, small x, equal to f prime of x, dx, sorry, this is dx, not dt. So if you compare these two, the difference is that we don't have the second term here. Okay? So this x here is the term in this. So this is by deterministic calculus, and this one here is random. And here you can see the difference. It's very clear that why Ito's formula is needed, because we have one extra term. Okay, is there any problem here? So it's better to keep this table in your mind, this little table, and you can use this for your stochastic calculus, and it will be very useful. Now, what I would like to remember as Ito formula is this one-dimensional formula here, okay? But this can be simplified. If you substitute this by dxt, then you can simplify this further. It doesn't matter which one you memorize. In either case, you will get the same result. Okay? Now we will do that, and you will see how. All right, so we saw that the second, the third term and beyond does not matrices, and we have our Ito formula. But as I told you, you can simplify this more. So d of f of xt equal to f prime of xt times d of xt that we know is zt dt plus sigma plus yt d of dt plus half of f double prime of xt times dxt squared, but we calculate dxt squared. It's y2 yt squared dt. Okay? Now you can reorder the terms and put all dt term together and all ddt term together. So it would be f prime of xt zt plus half of f double prime of xt yt squared times dt plus, and we have only one term that contains dt, which is f prime of xt yt dr. So this is nothing really strange, it's just a simplification of the Ito formula. Okay? So you can either memorize this one, or you can either memorize this simpler formula here. And it's really up to you. It's a personal preference that which one you like to memorize. For me, it's much simpler to memorize this formula here. But you can memorize either one. So this is the formula that's discussed also in section 9.3.1, and you can see it's almost what we did here. And finally, this is the formula that we obtained. So like in the note, it's zt times f prime. Here we have f prime times zt, but it's not really much. Okay, now the next is how we can apply this in examples. All right, so Ito formula by itself is important, but it's more important to know how we can apply it in examples and solving a stochastic differential equation. So that's what we will do for the rest of this lecture. Okay, any question? All right, 9.3.2, which is basically an example that we already saw. So here we would like to calculate integral 0 to t ds d of ds. Okay. So last session we saw that this is not equal to half of dt squared. But if it's not equal to half of dt squared, then what's the precise expression? And that's what we calculate now, okay? So define f of bt by bt squared. So this means that you have a deterministic function f of x equal to x squared, and you substitute x by b. Be careful that this t here is dependent on b, so you substitute the whole of b by x. So your actual function is x squared. It's not x index t squared, okay? So this is the function that you have. Now calculate d of f of bt by Ito formula, okay? So I'll add the Ito formula again. It's f prime of bt d of bt plus half of f double prime of bt d dt squared. Okay? So this is exactly aligned with this formula. Instead of x, we have d. Okay? So here the original stochastic process is d of xt equal to d of dt. So it's very simple. Okay, it's a very simple process. And we want to calculate d of f of dt. So you apply the Ito formula, which is f prime of dt plus half of f double prime of bt ddt squared. Any problem with this application? So I just applied the Ito formula directly, but instead of xt, I use dt. Remember that xt is given by this general formula. D of xt equal to mu of dt plus sigma d of dt. But here there is no mu. Mu is 0 and sigma is 1. Okay? So it's a very simple and special case of this original formula. So mu is 0 and sigma is 1. Now if prime of x is 2x, so this is 2 bt d of dt. So if prime of x is 2x, if double prime of x is just 2. And you substitute x by bt, so 2 bt d of bt plus half of, if double prime is just 2 times 2 times dbt squared is dt, right? So this is, therefore we obtain that d of f of bt, which is bt squared, is 2 bt d of bt plus just dt. 2 and 2 cancel, and we get only. Now, in order not to be confused with the index t, I just do a little change of index, d of s squared. So I just change t to s for simplicity. 2 of ds, d of ds plus d of s. Okay? So this step is nothing. I just change t to s. Why I do that? Because in the next step, I want to integrate from 0 to t. All right. So now take the integral from 0 to t. So integral 0 to t, integral 0. So that's why I changed t to s, because I didn't want to be confused with the notation. Now integral from 0 to t dds squared is bt squared minus b0 squared equal to 2 is a constant, integral 0 to t ds d of ds, and integral 0 to t ds is t. Plus so b0 squared is 0, because by definition of Brownian motion, we start from 0. And we know that b0 is also 0, so this term is gone. And from here we get integral 0 to t ds d of ds is equal to half of dt squared minus t, or dt squared divided by 2 minus t divided. So you can see that integral 0 to t ds ds is not just half of bt squared. We have also an additional term, minus half of t. Here it's better to write just integral instead of ds squared. Right, it's better to write d of dt squared. That's a much better notation. Okay? So you just take integral, and you don't need to change it actually. You just take integral of both sides. And integral 0 to t S squared is bt squared minus b0. Or you can use the notation fs here because after all that's your function here. So instead of bs squared, you can also write fs. So please change this notation because this is a standard notation that must be used. Just simply integral of those sides. So please make sure you understand all this process. If it's not clear, then ask. So if you can understand this example, the other examples are very similar. So again, the original function is deterministic function x squared. That's a deterministic function, okay? But what we want is bt squared, and bt is random, is not deterministic. But it can be defined by f of bt, where f is deterministic. Look, for f I use small f, but f of bt is just a random process. Okay, it's bt to the power of 2, where bt is Brownian. So the rest is just doing the calculation correctly, and if you do that, then you get the result. So the purpose of this example was to calculate integral 0 to t ds d of ds. So this is, I think, example. No, it's just section 9. Okay, now we solve one more example related to geometry, Brownian motion. So this is section 9.3.3. In this section, you have some examples that you can try them by yourself. Okay. The one that here I would like to discuss is example 3. Okay. We have d of xt equal to xt mu dt plus sigma d of dt. Mu and sigma are constant. Mu and sigma are constant. And we call this a geometry Brownian motion. Geometry Brownian motion. Okay, now let fx be log of x, okay, deterministic function f, and we want to calculate d of f of xt. This is what we want to calculate. And again, we use Ito formula. So this is the purpose of this example. So I don't want to raise the Ito formula. You can always see it there. I did a calculation. So again, d of f of xt is f prime of xt. So here we have fx equal to log of x. So f prime of x is 1 over x. F double prime of x is minus 1 over xt. Okay? So we have f prime of x, which is 1 over xt. D of xt plus half of f double prime of x, which is minus 1 divided by xt squared, and then we have dxt squared. So this is by Ito formula, and your next step is to simplify this. Okay. 1 over xt, and what's the formula for dxt? It's xt times mu dt plus sigma d of dt, then minus 1/2 1 over xt squared times dxt squared. So here you can calculate dxt squared by the similar way that we did it before. You can see that dxt squared is, so this would be xt times mu dt squared, which is ignorable, xt mu dt plus xt sigma d of dt. Now look, we want to calculate the square of this. So the first term would be xt to the power of 2, mu to the power of 2 times dt to the power of 2. That is 0, right? Because dt squared is 0. I write it for the last time, x2 mu2 dt squared, then plus 2 of xt mu xt sigma dt dt, and then plus square of the last term, which is xt squared sigma squared d dt squared. So from here, dt squared is 0, dt times dbt is 0, dbt squared is dt, so this would be sigma squared xt squared dt. And therefore, this would be sigma squared xt squared dt, xt squared. Okay, next you simplify. So here we have xt and xt cancel. It's just dt plus sigma d of dt minus xt squared and xt squared cancel. So it will be sigma divided by 2 dt. Okay, and the last step is just to put the term together. So d of xt is mu minus half sigma 2 dt plus sigma d of dt. Okay, so this is so can someone point out one problem here? So one technical problem is in Ito formula, if because we have f prime, we have f double prime, right? So f must be twice differentiable. So in Ito formula, we say that f must be belong to C2 or twice differentiable. Okay? Or 2 times differentiable. But here we have f equal to log of x. The first derivative is 1 over x. 1 over x at time 0 is not definable. So this f is not actually twice differentiable because it has a problem at point x equal to 0. So in fact, we could not apply Ito formula that easily here because of this technical problem that f is not twice differentiable. But we keep everything simple. This is a technical problem, and it will get us the right answer. So we just ignore that. Okay? But it's better to know that. Okay, is there any question, problem? So the next example find the solution of dxt divided by xt equal to mu of dt plus sigma d of dt. Okay, given time So it means that, let's say that time 0 is clear for us, okay? We're given x0, given x. So this means that x0 is a constant. You know exactly the value of x0. So do you remember this process? This was the start value process that we studied, right? We just used the notation s instead of x, but it's exactly the same thing. And I showed you the solution. I told you that the solution is equal to this. And now you can actually find out the solution. Okay? Do you have enough time? So there could be two solutions. Like solution 1, we just use this example here. So in this example, we showed that d of log of xt is equal to mu minus half sigma dt plus sigma d of dt. So this was from this solution, from this example. Okay, so this is coming from. Now take the integral of both sides. So I skip the details. First you change t to s and take integral, and then you will get log of xt minus log of x0 equal to integral 0 to t u minus half of sigma to dt plus integral 0 to t sigma dvs. So change the inner to this. Okay, so I just took the integral of both sides. And now log of xt minus log of x0 is log of xt divided by x0 by the properties of log. Now mu and sigma were constant, right? So here mu, just to emphasize, mu and sigma are constant. Okay, exactly like the previous example. So mu minus half of sigma 2 is just a constant. We take it out. And integral 0 to t ds is t plus, again, sigma is a constant. And integral 0 to t dds, we discussed that. It's bt minus v0, and we know that v0 is 0. So from here, xt divided by x0 will be e to the power of mu minus half of sigma to t plus sigma bt, or xt equal to x0 e to the power of mu minus half of sigma to t plus sigma of bt. And we got the solution. Okay? So in the previous chapter, we accepted the solution, and this is how we can obtain the solution. So that's why that Ito's formula is such a powerful tool, because it will let you to solve a stochastic differential equation, something that you cannot do with the classical or deterministic calculus. So is there any problem here? So to be honest, it's not very difficult, right? It's just you have to follow the formula correctly, do the calculation, and it will get you what you want. However, there is a very important point with this example. Because if you look at the previous example, we started with a function fx equal to log of x, right? So I wrote it here for you. Fx equal to log of x, then we calculated the differential of log of x, okay? And we use that to find the solution of these stochastic differential equations. The point is that why log of x, Okay? So where this log of x is coming from. If you cannot guess that, then it's not easy to solve this kind of problem. And that's a challenge with stochastic differential equation. So again, to summarize, in order to solve this stochastic differential equation, we started with log of x, xt. We obtained the differential of log of xt, and then these lead to solution. Okay? But why log of xt? Why not e to the power of xt? Okay? So this is a challenge with the stochastic differential equation, that you have to start with the right function. So instead of log, here you use exp of xt, or you use sine of xt, or cosine of xt. You can do the calculation, but it doesn't lead to the solution. Okay? Try that, like use xt cubed, use xt squared, and you will see that that doesn't give you the solution. So guessing this starting function is very critical in order to find the solution of the stochastic differential equation. And unfortunately, there is no rule for that. So it's just a good guess. Okay? But tomorrow I will show you some little tricks that can help you to guess these initial functions, and then help you to find the stochastic differential equation. Now the solution too would be, you don't discuss it, but you can do it yourself. Calculate dxt for xt equal to x0 e to the power of mu minus sigma divided by 2t plus sigma dr. Okay? So here you assume that you know the solutions, because I told you, right? And in chapter 8, I told you that this is the solutions. So in order to solve that, you just take dxt and you prove that it satisfies these equations. So we say that calculate dxt for these process. So that's something that it would be interesting for yourself to do, and you have it, I think, in your notes as well. So if you have trouble, you can consult it. But solution 1 is better than solution 2, because in solution 2 you assume that you know the solutions. Okay? And then you just check it. So you say calculate dxt for this and check that it satisfies star. And this star is this equation. But solution 2 is based on this assumption that you know the solution, and we already know that because I told. And in order not to be confused, in your node, instead of bt, sometimes it's written as square root of t x, where x is normal of 0 and 1. Okay, so instead of bt, you have square root of tx, x is normal of 0 and 1. These two have the same distributions. So when we talk about distributions, like expectation, these are the same. But in this chapter, we would like to write bt. In the previous one, it was like square root of tx. Because if you calculate the variance of square root of x, it would be square root of t to the power of 2. Look, variance of square root of t times x would be square root of t squared times variance of x. And square root of t squared is t. Variance of x is 1 because it's standard, so it gives you t. So these two in distributions are the same. Okay? So this x is not this xt here. Okay? It's just a normal distribution, standard normal distribution. Maybe it's better to use y. So y and variance of. So instead of bt, sometimes you see the square root of t times a standard normal distribution. Both of them are the same. Alright, if you have any question, you can ask.